The infant universe held a secret it should not have been able to keep. Supermassive black holes, cosmic giants weighing billions of times our sun's mass, were already in place when the cosmos was a mere toddler. This profound mystery defies our fundamental laws of physics, forcing a complete rethinking of cosmic evolution. By the end of this journey, you will understand the leading theories, from direct collapse to exotic early conditions, that explain how the impossible became real. How did these titans form against such impossible odds, and what rare cosmic cradle could nurture them? What does the existence of these ancient giants tell us about the very nature of reality? How much of our universe's story is still waiting to be uncovered? The clock was already ticking against them. In a cosmos only a few 100 million years old, the first stars had barely ignited. Yet the light from quasars like J1342 plus 0928 tells us a different story entirely. This beacon, whose journey to our telescopes began over 13 billion years ago, is powered by a black hole of staggering proportions, weighing 800 million times the mass of our Sun. For such a colossus to exist so early, it had to grow at a pace that breaks the rules. Physicists call this the Eddington limit, a cosmic speed governor for how quickly a black hole can steadily feed. To reach the masses we observe, these early giants would have needed to consume matter at a ferocious, nearly impossible rate for their entire existence. This is the timeline crisis in its purest form. There was no time for a slow and steady diet. The standard model of a small star collapsing into a black hole and then slowly growing simply does not work here. The math does not add up. As leading theorist Priyamvada Natarajan has pointed out, this pushes the very limits of our physics. The existence of these ancient quasars is not just a curious fact, it is a direct challenge. It forces a fundamental question. What kind of seed could possibly bypass this entire slow growth process? What kind of monster was born not as an infant, but as a ready-made giant, already holding the keys to a cosmic kingdom? So the very first black holes, the ones born from dying stars, faced an insurmountable problem. They were simply born too small. Picture a single grain of sand, and then picture a mountain. That is the scale of growth required for a stellar mass black hole to become a supermassive one. The physics governing this growth, the Eddington limit, acts like a cosmic regulator. As a black hole feeds, the infalling matter gets incredibly hot and bright, radiating intense light. This radiation pushes outward, actually preventing more material from falling in. It is a self-regulating diet, a maximum sustainable feeding speed. Even if a stellar seed ate a constant, perfect meal at this absolute maximum rate for hundreds of millions of years, the math is brutal and unforgiving. It could never reach the billion solar mass titans we see lighting up the infant cosmos. The time just was not there. This is the heart of the seed problem. We are not just missing a piece of the puzzle, we are missing the entire first section of the picture. The starting point itself is wrong. This realization led visionary thinkers like Martin Rees to propose a radical alternative. What if the universe skipped a step? What if, instead of a star dying to create a small black hole, an entire cosmic cloud collapsed directly into a heavyweight champion from its very first breath? This is the direct collapse model, a theory that rewrites the very beginning of a black hole's life. This theory rewrites the cosmic rulebook on how a black hole is born. Instead of a stellar corpse, the first step is a colossal cloud of pure hydrogen and helium, a pristine remnant from the Big Bang itself. For this cloud to collapse into a single, massive object, it must avoid a critical pitfall: it cannot break apart. Normally, as a gas cloud collapses, it heats up, and this heat causes the cloud to fragment, birthing a cluster of stars rather than one single giant. The key to preventing this fragmentation lies in the chemistry of the gas itself. If the cloud contains molecular hydrogen, it acts as an incredibly efficient coolant, allowing dense knots to form and pull away, dooming the cloud to become a nursery of small stars. But in the direct collapse model, a powerful external force intervenes. Imagine a neighboring galaxy, one of the very first, blazing with intense ultraviolet light. This radiation floods the primordial cloud, breaking apart the molecular hydrogen and stripping away its cooling ability. Without this coolant, the gas cannot fragment. The heat builds, the pressure rises, and the entire vast cloud, weighing hundreds of thousands of solar masses, is forced to collapse as one monolithic structure. The result is not a star as we know it, but a supermassive star, a behemoth with a fleeting existence. Its core burns furiously for perhaps only 1,000,000 years, a mere blink in cosmic time, before its own immense gravity causes a catastrophic collapse. There is no violent supernova explosion to scatter its material. Instead, the entire star implodes silently and completely, directly into a black hole with a seed mass of tens of thousands of suns. This is the giant seed, a ready-made foundation that can then grow at a sustainable pace to become the supermassive titans we observe. Computer simulations, like those pioneered by Mohammed Latif, show that these events are not common. They require a perfect storm of conditions, a rare, dense cloud bathed in just the right amount of radiation from a nearby source. This elegant solution to the timing problem hinges on a cosmic environment that was uniquely violent and pristine, a paradox that makes these seeds both necessary and incredibly rare. So what were these special cosmic cradles actually like, and how did they forge such impossible giants from the raw chaos of the early universe? But for this cosmic sterilization to work, the recipe demands incredibly specific ingredients. A primordial gas cloud must be pristine, untouched by the nuclear furnaces of earlier stars. This means no elements heavier than hydrogen or helium, nothing that could act as an alternative coolant. The real culprit to eliminate, however, is molecular hydrogen. Just a trace amount of this simple molecule, two hydrogen atoms bound together, acts as a super-efficient cooling system. It allows the gas to shed heat, condense, and inevitably shatter into countless smaller stars. To forge a single giant, you must first disarm this cooling mechanism. This is where a special kind of ultraviolet light, known as Lyman-Werner radiation, enters the story. Emitted by the hottest and most massive of the first stars, this radiation has just the right energy to break apart the molecular hydrogen bonds. It bathes a nearby cloud in a destructive light, stripping away its ability to cool and fragment. Think of it not as a creative force, but a destructive one that paradoxically enables a greater creation. It sterilizes the cloud, preventing the birth of a star cluster, and forcing the entire structure to collapse in on itself as one unified, monstrous entity. This reveals a profound cosmic interdependence. The very first stars, blazing briefly and violently in their dark matter halos, become the midwives for the first supermassive black holes. Their death in a supernova would have polluted the environment with heavy elements, ruining the pristine conditions needed for direct collapse. But their life, their intense ultraviolet light, prepares the cradle for a different kind of giant. It is a delicate and fleeting balance, a Goldilocks condition where one cosmic event must occur just close enough and just at the right time to trigger another. This fine-tuned interplay forces us to look at the cosmic structures that could possibly host such a rare and spectacular event. This perfect storm requires a stage of immense gravitational power, a cosmic arena built from the universe's most mysterious substance, dark matter. In the young cosmos, dark matter was not evenly distributed. It clumped together into vast structures known as halos, immense invisible spheres that acted as gravitational anchors. For a direct collapse black hole to be born, an ordinary halo would not suffice. It needed to be a truly massive one, a heavyweight champion among these invisible constructs. These colossal halos possessed a deep and powerful gravitational well, one capable of pulling in staggering amounts of pristine primordial gas from the surrounding void. But even this was not enough. The gas itself had to behave in a very specific way. If the gas cloud had too much spin, it would simply form a rotating disk rather than collapsing inward. The ideal candidate was a halo with low angular momentum, where the incoming gas did not carry much rotational energy, allowing it to flow directly toward the center. Furthermore, these special halos reached what scientists call a virial temperature above 10,000 Kelvin. At this extreme heat, a different cooling process takes over. Instead of molecular hydrogen cooling the gas and causing fragmentation, atomic hydrogen begins to emit radiation, allowing the gas to cool just enough to condense, but not so much that it shatters. This leads to a monolithic, coordinated collapse of the entire gas reservoir. We call these atomic cooling halos, and they are the theorized perfect cradles for the universe's first supermassive black hole seeds. Their rarity in the early universe is a key piece of the puzzle, explaining why every galaxy did not end up with one of these ancient giants at its core. This theory beautifully weaves together the birth of the universe's largest structures, the dark matter halos, with the formation of its most enigmatic objects. Yet, direct collapse is not the only pathway scientists are exploring. Another compelling theory suggests that the seeds of these monsters were sown not in isolated clouds, but in the frantic, crowded centers of the very first star clusters. Perhaps the seeds were not born giants, but learned to feast like them. Another compelling theory suggests that early black holes did not need to bypass the standard growth limits, but instead discovered a way to shatter them. This is the model of super-Eddington accretion, where the rules of cosmic consumption are rewritten. The standard Eddington limit assumes a neat, orderly process, with matter falling in a thin, flat disk. But the early universe was a place of chaos and immense density. In such an environment, the accretion disk around a young black hole would not be a delicate plate. It would be a thick, puffy donut, a swirling maelstrom of gas so dense that it becomes a trap, not just for matter but for light itself. Within this chaotic structure, a critical phenomenon called photon trapping occurs. The radiation produced by the infalling matter, which normally pushes outward to halt the feast, becomes ensnared in the incredible density of the flow. It cannot escape to exert its pressure. Instead, the radiation is dragged inward along with the gas, a silent prisoner in its own cosmic downfall. This allows the black hole to consume matter at a rate far exceeding the supposed speed limit. Think of it not as a steady, disciplined diet, but as a series of violent, almost gluttonous growth spurts. The black hole experiences brief, hyper-efficient binge-eating episodes, rapidly packing on mass in a geological instant. While this process does not solve the initial seed problem on its own, it dramatically shortens the growth timeline for an intermediate mass seed. A seed of a few hundred solar masses could, through these feeding frenzies, balloon into a supermassive giant much faster than traditional physics would allow. We even see hints that this is possible in our modern universe. When a star wanders too close to a black hole and is torn apart in a tidal disruption event, The resulting influx of material can sometimes mimic this super Eddington accretion, a fleeting echo of the feasts that built the ancient titans. This model adds a crucial layer of complexity, showing that how a black hole eats can be just as important as what it is born as. And this chaotic, violent feeding naturally brings us to another powerful force that could have accelerated their growth: the immense power of cosmic collisions. The early cosmos was a crowded and violent dance floor. In the dense environments of the first protogalaxies, collisions were not a possibility, they were an inevitability. This introduces a fifth theory, the merger tree, where giants are built not from a single seed, but from the relentless assembly of many smaller black holes. Imagine a chaotic construction site where entire buildings are constantly crashing into one another, fusing into ever larger structures. This is a bottom-up approach, a stark contrast to the top-down direct collapse of a single monolithic cloud. Each time two small galaxies merged, their central black holes would be drawn together by gravity, eventually spiraling inward and combining into a single, more massive object. But the true power of a merger goes beyond simply adding two masses together. The immense gravitational shockwaves from such an event send tsunamis of gas and dust rushing toward the new central black hole, triggering the kind of super Eddington feeding frenzies we just discussed. It is a 1-2 punch, a growth spurt fueled by both a merger and a subsequent feast. For this process alone to build a billion solar mass titan in just a few 100 million years, however, the initial conditions would have to be extreme. The universe would need a veritable sea of black hole seeds, and the merger rate would need to be almost impossibly high, a constant, frantic cascade of collisions. While this hierarchical buildup is a fundamental force in cosmic evolution, it struggles with the sheer speed required by the most ancient quasars. Yet it highlights a crucial truth: the dynamic, chaotic environment of the young universe itself was a powerful engine for growth. This brings us to the final exotic frontier, a theory that looks back to the absolute beginning, to the nature of the very first stars themselves. The very first generation of stars may have been the ultimate cosmic heavyweights. These are called population 3 stars, and they were unlike anything that exists today. Born from the universe's pure, uncontaminated hydrogen and helium, they contained no heavy elements to act as internal stabilizers. This allowed them to grow to truly monstrous sizes, potentially reaching up to 1,000 times the mass of our Sun. But the theoretical extremes are even more breathtaking. Some models suggest that under the perfect, almost impossibly calm conditions of a non-rotating spherical collapse, a single star could swell to 100,000 solar masses. A single star shining with the light of a small galaxy. Its life, however, would be spectacularly brief, burning its nuclear fuel at a ferocious rate. Such a supermassive star would shine for only a few million years before its own immense weight became unsustainable. Its core would then collapse, not in a supernova that scattered its enriched remains across space, but in a quiet, total gravitational failure. The entire star would vanish, leaving behind a black hole seed of staggering proportions, tens of thousands of times more massive than the remnant of an ordinary star. This pathway elegantly blurs the lines we have drawn, suggesting that the first stars were not just predecessors, they were the very seeds themselves. Their silent, implosive deaths would have sown the cores of galaxies with ready-made giants, bypassing the slow growth problem entirely. Yet, this process too required a cosmic cradle of perfect stillness, a pocket of the early universe undisturbed by the turbulent spin that typically governs gas clouds. The rarity of such conditions explains why these events were not the norm, but their possibility offers a profound clue. It tells us that the answer to our cosmic mystery might not lie in one single theory, but in a combination of them all, a tapestry of rare and violent births woven together in the darkness of the young cosmos. Perhaps the seeds were not forged from ordinary matter at all, but from the universe's most dominant yet elusive substance, dark matter. This speculative theory proposes that certain exotic forms of this mysterious material could have behaved in a unique way, clumping together and collapsing under their own powerful gravity to form massive black hole seeds directly. Another candidate from the fringes of cosmology is the primordial black hole. These would not be the remains of dead stars, but artifacts of the Big Bang itself, born from intense density fluctuations in the universe's first chaotic moments. If these primordial black holes were born with the right mass, perhaps ranging from the mass of a mountain to that of a star, they could have been scattered throughout the cosmos, serving as ready-made building blocks. This idea ventures deep into theoretical physics, connecting the unimaginably small quantum ripples of the infant universe to the colossal giants that would later anchor galaxies. While these concepts remain highly speculative, they demonstrate the profound reach of this mystery. The existence of ancient supermassive black holes is such a fundamental challenge that it pushes us to question the very laws we hold as certain, forcing us to consider possibilities that lie beyond our current standard models. It reveals that the answer may not just be hidden in the darkness of space, but in the darkness of our own understanding. To move from these theoretical frontiers back to observable evidence, we must rely on the most powerful time machines ever built. Theoretical possibilities are now colliding with hard, empirical evidence. The James Webb Space Telescope, with its unparalleled infrared vision, is acting as a cosmic time machine, peering back into the era when the first supermassive black holes were taking shape. It is not just seeing ancient light, it is taking a census of the infant cosmos, identifying a surprising number of faint galaxies and brilliant active galactic nuclei from a time known as the epoch of reionization. Each of these points of light is a data point in a grand cosmic investigation. By carefully measuring the masses of these early black holes and calculating how quickly they were consuming matter, Webb's data provides the ultimate test for our competing theories. Does the population of black holes we see match what the direct collapse model predicts? Or does their sheer number suggest a different, even more efficient pathway? This is no longer just a thought experiment, it is a race to match prediction with observation. Meanwhile, giant ground-based arrays like ALMA, the Atacama Large Millimeter Array, examine a different piece of the puzzle. While Webb sees the black holes themselves, ALMA studies the cosmic cradle, mapping the dynamics of the cold gas reservoirs in these early galaxies. It reveals how gas flows, collapses, and fragments, showing us the exact conditions that could or could not give birth to a massive seed. The ultimate goal, the smoking gun, would be the detection of an object that is too massive and too compact to be a star cluster, yet resides in a galaxy too young to have built it through slow growth. It would be an object that simply should not exist under the old rules, a pristine black hole seed caught in the act of formation. Every new observation has the power to validate one theory and dismantle another, forcing our models to evolve or be replaced. This empirical journey leads us to a profound realization, one that reshapes our entire understanding of cosmic history. Every elegant solution we have devised seems to fray at the edges when confronted with the full complexity of the cosmos. The direct collapse model, for all its beauty, demands a cosmic lottery win, an alignment of pristine gas and perfect radiation so rare that we struggle to believe it could account for the multitude of ancient giants Webb is now revealing. If this was the primary pathway, the early universe must have been dotted with these special sterilized cradles far more often than our simulations predict. Eddington accretion offers a way to fast-track growth, but it raises its own difficult questions. How stable are these thick, puffy accretion disks? Can a black hole truly sustain such a gluttonous feast without the intense radiation and powerful outflows, eventually choking off the fuel supply itself? It is a cosmic binge that risks starving the very organism it is trying to feed. The hierarchical merger model, while a fundamental force in galaxy evolution, faces the relentless pressure of the cosmic clock. Building a billion solar mass titan through a slow cascade of collisions is like trying to win a race by constantly stopping to tie your shoes. The process is simply too slow to explain the quasars we see blinking into existence when the universe was less than a tenth of its current age. Perhaps the most profound contradiction lies in the relationship between a black hole and its home. As a black hole feeds and grows, it unleashes torrents of energy and radiation that flood its host galaxy. This intense feedback can blow away the surrounding gas reservoir, the very material needed for both new star formation and the black hole's own future meals. It is a self-limiting process, a case where the entity's own success can stunt its growth and reshape its entire galactic environment. These are not minor gaps in our knowledge, they are fundamental tensions at the heart of astrophysics. Each theory, when pushed to its limit, reveals a flaw that forces us to think more creatively. This ongoing struggle is not a sign of failure, but the very engine of scientific discovery. The existence of these early supermassive black holes is not a puzzle with one missing piece. It is a signal that our entire picture of cosmic dawn may need a subtle, yet profound, adjustment. These cosmic giants were not passive residents of the early universe, they were its architects. The furious energy pouring from a young quasar did more than just announce its presence, it fundamentally reshaped its entire galactic environment. This is the profound principle of co-evolution, a cosmic feedback loop where the black hole and its host galaxy grow together, locked in a gravitational and energetic dance. As a supermassive black hole feasted, it did not do so quietly. The intense radiation and powerful jets erupting from its poles flooded the surrounding space, heating vast reservoirs of cold gas. This heating prevented that gas from cooling and collapsing to form new stars. In essence, a voracious black hole could put its own galaxy on a strict diet, regulating the birth of future stars and ultimately limiting the galaxy's final size. A monster at the center held the power to dictate the fate of its entire cosmic home, but the influence of these early titans reached far beyond their own galactic borders. Their brilliant light played a pivotal role in one of the universe's greatest transformations, the epoch of reionization. For hundreds of millions of years after the Big Bang, the cosmos was filled with a thick fog of neutral hydrogen gas. The light from the very first stars began to burn off this fog, but it was the blazing beacons of the first quasars that finished the job. Their extreme ultraviolet radiation acted like a cosmic ultraviolet lamp, stripping electrons from hydrogen atoms across the vast intergalactic medium. They helped clear the cosmic fog, rendering the universe transparent to light and shaping the cosmos we observe today. This means the very existence of galaxies we see, including our own Milky Way, was influenced by the explosive growth of black holes in the ancient dark. Their early formation forces a complete recalibration of cosmic history, suggesting that the seeds of the largest structures were planted far earlier and grew far faster than we ever imagined. To truly grasp this, we must peer into the specific, violent cradles that made such rapid growth possible. We find these ancient titans not in isolation, but at the violent hearts of cosmic cities. The host galaxies for the earliest supermassive black holes were not the majestic, tranquil spirals we see today. They were compact, chaotic, and seething with raw energy. Picture a stellar metropolis 100 times denser than our present-day Milky Way, a place where gas clouds collided with furious intensity, igniting new stars at a rate that would dwarf our own galaxy's quiet output. In these frenetic cores, the conditions were not just ripe for growth, they were an all-you-can-eat buffet for a hungry black hole. The sheer density of gas flowing into the galactic center meant the central black hole was constantly surrounded by fuel, enabling the kind of rapid, sustained feeding required to reach such impossible masses so quickly. This intense star formation and the black hole's own growth were two sides of the same coin, a coordinated explosion of activity that built the galaxy's central bulge and its dark heart in tandem. The dynamics in these cramped, violent nurseries were a perfect storm. High gas densities provided the fuel, frequent gravitational interactions from mergers funneled that fuel inward, and the immense collective gravity of the crowded stars created a deep well from which nothing could easily escape. It was a self-reinforcing cycle of cosmic construction happening at a breakneck pace. By studying the light from these host galaxies with the James Webb Space Telescope, astronomers can uncover vital clues about the black holes they hide. The motions of stars and gas at the galaxy's very center, for instance, allow scientists to weigh the invisible gravitational anchor pulling on them, revealing the black hole's mass. The specific colors and intensities of the light can tell us if the black hole is in a quiet phase or in the midst of a ferocious feeding frenzy, actively accreting matter and blazing as a quasar. These galactic properties are not just background details, they are critical boundary conditions. Any successful theory for how supermassive black holes formed must be able to explain why they are found in galaxies with these specific traits: compact, gas-rich, and furiously building. The galaxy and its central monster are an inseparable pair, two partners in a dance that began when the universe was in its infancy. To truly understand the limits of this partnership, we must look toward the most extreme examples, the brightest and most violent objects the cosmos has ever produced. The quasar known as J0313-1806 stands as a definitive cosmic challenge. Its light, a traveler for over 13 billion years, shows us a universe that was a mere 670 million years old. At the heart of this beacon rests a supermassive black hole of almost incomprehensible scale, a colossal anchor of 1.6 billion solar masses. To find such a fully formed titan so soon after the dawn of time defies every comfortable assumption about cosmic growth. This single object, a record holder for its distance, is more than a point of light. It is a profound question written across the sky. Its spectrum, the unique fingerprint of its light, reveals a host galaxy in a state of ferocious creation, birthing stars at a rate hundreds of times greater than our own Milky Way. Yet this frantic stellar nursery is not a peaceful place. The data also shows powerful winds, vast outflows of gas being blasted away from the galactic center at tremendous speeds. These are the winds of the black hole itself, the visible proof of its energetic feedback as it feasts. This celestial object becomes a perfect laboratory, a natural experiment testing the absolute limits of our theories. Could a direct collapse seed have grown this massive so quickly? Would even super Eddington accretion be enough? The sheer mass of this black hole, combined with the youth of its universe, pushes every model to the breaking point. It is the ultimate poster child for the early universe mystery, a constant reminder that our most elegant ideas must still account for the most extreme examples nature has to offer. While we focus on gravity and radiation, a silent, invisible force may have been pulling the strings all along. Magnetic fields, often overlooked in the grand story, could have been the secret conductors of the early universe's greatest growth spurts. To understand how, we need to look at a fundamental problem in any accretion disk. The gas swirling around a black hole carries a property called angular momentum, a kind of cosmic spin that prevents it from falling straight in. It is like water circling a drain, reluctant to make the final plunge. Left to its own devices, this gas would orbit for an impossibly long time. So how does it finally cross the event horizon? The answer may lie in a powerful process called magnetorotational instability. Imagine the swirling disk of gas as a series of cars on a circular racetrack. The inner cars want to move faster than the outer ones, creating a natural shear. Now, thread that entire track with a magnetic field, like connecting all the cars with invisible, elastic ropes. As the inner cars pull ahead, they stretch these magnetic ropes, transferring energy and momentum from the inner parts of the disk to the outer regions. This magnetic friction saps the gas of its orbital energy, allowing it to spiral inward toward the waiting black hole far more efficiently than gravity alone could manage. In the dense, chaotic environments of the first galaxies, conditions were perfect for this process to run wild. Turbulent motions could have amplified weak seed magnetic fields to incredible strength with breathtaking speed. This magnetic enhancement would have turned a steady trickle of matter into a raging river, enabling the kind of hyper-efficient accretion that could build a billion solar mass giant in a cosmic instant. This introduces a whole new layer of physics to the mystery, a branch known as magnetohydrodynamics, where the behavior of plasma and magnetic fields become inseparable. Unraveling this magnetic influence is one of the most complex challenges in modern astrophysics, requiring some of the most sophisticated supercomputer simulations ever run. These digital universes must model how tangled magnetic fields twist, snap, and reconnect, all while governing the flow of matter on a precipice of oblivion. It suggests that the true cradle of a supermassive black hole was not just a place of immense gravity, but a crucible of cosmic magnetism, where invisible lines of force orchestrated the final, furious fall. We test these cosmic theories not with telescopes alone, but with digital universes born inside supercomputers. These are not simple animations. They are full-scale cosmological simulations, mathematical engines that attempt to replay the entire history of the cosmos from its first moments. Using sophisticated codes like ARIPO and ENSO, scientists can program in the known laws of physics, from gravity and fluid dynamics to the complex chemistry of primordial gas, and then set the simulation in motion. These digital realms track the evolution of dark matter as it clumps into halos, the flow of gas as it cools and collapses, the ignition of the first stars, and the subsequent birth and growth of black holes. They are our only true laboratories for the early universe. Within these virtual worlds, we can run experiments that are impossible in reality. We can create 1 million different versions of cosmic dawn, tweaking a single variable each time. What happens if we increase the density of a gas cloud? What if we remove the radiation from a neighboring galaxy? Does direct collapse still occur, or does the cloud simply shatter into 1,000 small stars? The simulations provide a statistical answer, showing us not what must have happened, but what pathways are most likely to lead to the supermassive black holes we actually observe. The resolution of these simulations is constantly improving, allowing us to zoom in from the scale of entire galaxy clusters down to the chaotic environment around a single growing black hole. This ever-increasing detail is crucial, as it allows us to see if super-Eddington accretion can be sustained in a turbulent disk, or how effectively magnetic fields can transport angular momentum and drive matter inward. The results are not perfect predictions of our specific past, but they are powerful probability maps. They guide astronomers, telling them where and what to look for in the flood of new data from observatories like the James Webb Space Telescope. The digital universe has become our primary testing ground, a place where we can witness the impossible becoming probable right before our eyes. This frantic stellar competition for fuel lies at the heart of the growth paradox. A galaxy's gas is a finite resource, and the formation of massive stars creates a powerful rival for the central black hole. These brilliant, short-lived giants do not just consume gas, they actively destroy the feeding grounds. Their intense radiation and fierce stellar winds act like a cosmic hurricane, heating the surrounding gas and driving it out of the galactic center. When these stars finally reach the end of their lives, their cataclysmic supernova explosions inject even more turbulence into the system, violently scattering the remaining fuel. This process, known as stellar feedback, can effectively starve a growing black hole, cutting off its supply of matter just as it begins to feast. For a supermassive black hole to form with such incredible speed, this natural galactic regulation had to be bypassed entirely. The gas needed to flow directly to the center, falling into the gravitational well faster than stars could coalesce and explode to stop it. One theory suggests that in the unique, dense environments of the first galaxies, gas could collapse in massive, unstable streams, channeling fuel directly to the core without first fragmenting into a multitude of stars. Alternatively, the black hole itself might have played a role in silencing its competitors. The intense radiation from an early quasar could have flooded its host galaxy, heating gas just enough to prevent it from cooling and collapsing into new stars, effectively suppressing star formation and reserving all the fuel for its own growth. This delicate balance, a constant tug of war between the birth of stars and the appetite of a black hole, is a critical puzzle. It reveals that a galaxy is not just a collection of stars and gas, but a complex ecosystem where different cosmic forces compete for dominance. To solve the mystery of the ancient Titans, we must understand how this competition was so decisively won by the black holes in the universe's first chapters. This leads us to an even more radical proposition, that the seeds for these giants were not forged in galaxies at all, but were primordial gifts woven into the fabric of space-time at the very moment of creation. The very fabric of the newborn universe may have been threaded with these seeds from the first moment. This is the theory of primordial black holes, a concept that pushes the origin story back before the first stars, before the first atoms, to the initial chaotic instance after the Big Bang. Imagine the cosmos not even a second old, a seething, dense soup of fundamental energy. Within this plasma, tiny quantum fluctuations, random ripples in the density of space-time, could have been stretched to enormous scales by a period of hyper-fast expansion known as inflation. In regions where these fluctuations were particularly intense, the density might have been so extreme that gravity overcame all other forces, causing a pocket of space to directly collapse into a black hole. These would not be the remnants of dead stars. They would be cosmic artifacts born from the raw energy of creation itself. For this theory to solve our supermassive black hole mystery, some of these primordial black holes would need to have been born with a significant mass, perhaps ranging from 1,000 to 1,000,000 times the mass of our Sun. Such heavy seeds would be perfect ready-made building blocks, already possessing the heft to grow into the billion solar mass titans we observe, completely bypassing the slow growth of stellar corpses. Their formation hinges on the precise nature of those first density fluctuations, a signature imprinted on the cosmos by the physics of inflation. This idea creates a breathtaking bridge, connecting the unimaginably small world of quantum mechanics to the grandest structures in the universe. A single microscopic ripple at the dawn of time could, through this process, become the gravitational anchor for an entire galaxy. While no primordial black hole has ever been definitively confirmed, their potential existence remains one of the most elegant solutions to the timing crisis. The search for them continues not just by looking at the distant past, but by examining our own cosmic neighborhood for their subtle, gravitational effects. This speculative pathway reminds us that the answer to the ancient giants might be found not in how they grew, but in how the universe itself was born. Quantum seeds of the universe were sown in its very first instant. During a fleeting epoch known as cosmic inflation, space itself expanded at an exponential rate, stretching microscopic quantum jitters across the cosmos. These tiny ripples in the fabric of reality were blown up to macroscopic proportions, becoming the gravitational blueprints for every galaxy, star, and planet to come. But what if some of these initial fluctuations were not just seeds for structure, but for the monsters themselves? In regions of exceptional density, the pull of gravity may have been so overwhelmingly strong that space collapsed directly into primordial black holes. This is not a story of stellar death, but of cosmic birth from the raw energy of creation. The specific characteristics of this inflationary period, its energy and duration, act like a cosmic dial. They would determine the mass spectrum of these potential black holes, dictating whether they were born as tiny specks or as ready-made heavyweights. This creates a breathtaking and direct link. The properties of the supermassive black holes we see lighting up the infant cosmos could, in principle, be a fossil record of the universe's first fraction of a second. The existence of certain ancient giants could validate one model of inflation over another, connecting the most enigmatic objects in space to the most fundamental laws of physics. Inflation may have provided the original blueprint for these cosmic architects. To move from this profound possibility to concrete proof, we must now search for the faint observational signatures these primordial seeds would have left behind. The ultimate prize in this cosmic treasure hunt would be an object of profound contradiction. We would be looking for a black hole of tens of thousands of solar masses, a heavyweight by any measure, yet it would be sitting in a galaxy that is strangely quiet and dark. This galaxy would emit very little ultraviolet light, the telltale signature of hot, young stars. That absence is the crucial clue. It means the star formation factory has been shut down, precisely the environmental sterilization required for a direct collapse. The intense Lyman-Werner radiation that forged the black hole seed also cleared the cosmic nursery, preventing new stars from being born. This object would not be a brilliant quasar. Its X-ray signature would be relatively soft, lacking the high energy punch of a more mature, rapidly accreting monster, and its spectrum would be clean, missing the broad, turbulent emission lines that signal a well-developed accretion disk. Astronomers are now scouring the deepest images from the James Webb Space Telescope for just such a candidate, searching for red, compact points of light that match this unique fingerprint. They are not looking for the brightest objects, but for the quiet ones with a massive secret at their core. Finding even a single, confirmed direct collapse black hole would be a landmark discovery. It would be the long-sought proof that the universe, in its youth, could indeed forge giants in a single, silent step. The detection of this cosmic unicorn would do more than validate a theory. It would open a direct window into the rarest of cosmic cradles, finally allowing us to witness the birth of a titan. The Eddington limit presents a cosmic speed limit, but even the strictest laws of physics have their loopholes. This fundamental barrier relies on two key assumptions: a perfectly spherical inflow of matter and a steady, unchanging state. The early universe, however, was a place of pure chaos where these pristine conditions almost never existed. In that turbulent environment, the geometry of how a black hole feeds becomes everything. If matter falls in not as a uniform sphere, but as a thin, dense disk, the radiation it emits can escape more easily from the top and bottom faces, rather than pushing back against the incoming flow. This simple change in shape can allow a black hole to consume matter at a slightly higher rate without choking on its own brilliance. But the real game changer is a phenomenon known as photon trapping. Imagine a waterfall of gas so incredibly dense and fast-moving that the light particles, the photons generated within it, become prisoners. They are physically dragged inward by the overwhelming flow of matter, unable to fight their way out to exert the outward pressure that defines the Eddington limit. In this scenario, the rules are not so much broken as they are rewritten by the environment itself. Some theoretical models suggest that through these mechanisms, a young black hole could experience brief, violent growth spurts, accreting at 10 or even 100 times the standard rate. This super Eddington accretion is not a magic trick. It is a more complex and realistic application of physics, where the opacity and structure of the inflowing material fundamentally alter the radiation dynamics. For a few fleeting moments, the cosmic governor is disengaged, allowing for a frantic binge that could add immense mass in a geological instant. Understanding these loopholes is not just a technicality, it is absolutely critical. The rapid mass assembly we see in the ancient quasars demands that we push these limits, exploring how the standard rules could be bent within the unique, violent crucible of the young cosmos. The universe's first stars were cosmic alchemists, fundamentally changing the chemistry of creation itself. Their violent death seeded space with the very elements that would eventually make planets and life possible, but this pollution came with a profound cost. It slammed shut one of the most important doors for building supermassive black holes. The key factor here is metallicity, a term astronomers use for the abundance of any element heavier than hydrogen or helium. In the pristine cosmos before the first stars, the metallicity was essentially zero. This purity was not a limitation, it was the secret ingredient. Primordial gas, made only of hydrogen and helium, cools very inefficiently. You might think efficient cooling is always good, but for forming a single massive object, the opposite is true. Inefficient cooling means the gas cannot easily shed its heat and collapse into many small, dense knots. It stays hot, puffy, and monolithic, perfectly poised for the coordinated collapse of a direct collapse black hole. Now introduce even a tiny sprinkle of metals from that first generation of supernova. These heavy elements, like carbon and oxygen, are spectacularly efficient at cooling. They act like a cosmic radiator system, allowing the gas to rapidly lose heat, contract, and inevitably shatter into a multitude of smaller stars. This fragmentation is the death knell for forming a single, massive seed. The gas cloud becomes a stellar nursery instead of a black hole womb. This means the window of opportunity for forming heavy seeds via direct collapse was cosmologically brief, perhaps only the first few 100 million years. Once the cycle of star birth and death began enriching the cosmos, this particular pathway effectively closed. The metallicity of a gas cloud became a decisive diagnostic, a simple but powerful rule. Low metallicity meant the potential for a monster seed still existed. High metallicity guaranteed the birth of a star cluster instead. The transition from a pristine to a polluted universe did not just mark the end of an era, it marked the end of an entire channel for creating the universe's most powerful objects. The next chapter of this cosmic mystery will be written with tools that are still on the drawing board, instruments designed to see the invisible and hear the silent. The Laser Interferometer Space Antenna, known as LISA, will open an entirely new sense for astronomers, listening to the faint ripples in space-time created by colossal collisions. When supermassive black holes merge in the distant void, they shake the very fabric of the cosmos, sending out gravitational waves that travel across billions of years. LISA will be sensitive enough to detect these echoes from the universe's first billion years, giving us a direct census of the black hole population during that critical era. The masses and merger rates it uncovers will tell us if the early cosmos was a quiet place with a few rare giants, or a chaotic symphony of constant, massive collisions. This is not just about seeing the light from these objects, it is about feeling their gravitational footsteps across time. Meanwhile, on the ground, a new generation of optical titans is taking shape. The 30-meter telescope and the extremely large telescope, with their colossal mirrors, will act like cosmic microscopes. They will dissect the light from the most distant quasars with breathtaking precision, a technique known as Chinese letter RESOLUTION spectroscopy. This will allow us to analyze the chemical composition of the gas swirling around these ancient black holes and map its turbulent motions in exquisite detail. We will be able to see the imprint of the black hole's gravity on its immediate environment, weighing it with unprecedented accuracy and understanding exactly how it is feeding. Is the gas flowing in smooth, dense streams, or is it a chaotic, magnetized storm? The answers are written in that starlight, waiting for a telescope powerful enough to read them. These observational leaps will be matched by a parallel revolution in the digital realm. The dawn of exascale computing, machines capable of performing a quintillion calculations per second, will allow us to build virtual universes of staggering complexity. Future simulations will not just include gravity and gas dynamics. They will weave in the intricate effects of magnetic fields, the turbulent energy of cosmic rays, and the detailed feedback from individual stars. We will be able to simulate not just one possible pathway, but the entire probabilistic landscape of cosmic dawn, seeing which combinations of physics naturally give rise to the giants we observe. This is the future of the hunt, a coordinated assault on the mystery using sight, sound, and silicon. Each new technological leap turns a speculative idea into a testable hypothesis, bringing us closer to the moment when we can finally point to a specific patch of sky and say, with confidence, that is how the impossible was born. A black hole is not the cosmic vacuum cleaner of popular imagination. Its gravitational pull is immense, but only within a specific boundary, its event horizon and the surrounding region of dominance. Outside this zone, objects can orbit a black hole just as planets orbit a star, held in a stable dance by gravity. The process of accretion, of matter actually falling in, is not a simple suction. It is a complex, violent ballet governed by two powerful forces, the angular momentum of swirling gas and the outward pressure of its own intense radiation. Matter desperately wants to orbit, not to fall, and it takes specific conditions to overcome that spin and allow the final, fatal plunge. This distinction is vital. It means the early universe could be packed with gas and stars that coexisted with a young black hole without being immediately consumed. The real mystery is not how everything was sucked in, but how specific rivers of gas were so efficiently channeled into the waiting mouth. Another idea that often surfaces is that the Big Bang itself forged these giants directly. While the theory of primordial black holes is a compelling scientific possibility, it is far from a proven fact. The conditions of the universe's very first moments are still a frontier of physics, and whether those conditions could produce black holes of the required mass remains an open question. Their existence is a hypothesis, not an established event. most importantly, the existence of these ancient supermassive black holes does not break the laws of physics. It feels that way because their rapid growth challenges the simplest models. But the true scientific pursuit is not about finding violations. It is about uncovering the specific, nuanced mechanisms that operated within the laws. We are not witnessing magic. We are being forced to look deeper into the rulebook, to chapters on magnetohydrodynamics, photon trapping, and chaotic accretion in dense environments. The universe is not breaking its own rules. It is showing us that our understanding of those rules, in the most extreme conditions, was incomplete. Dispelling these myths clears the air, allowing us to focus on the real, breathtaking physics at play, a puzzle where every piece must fit within the fundamental framework of reality. A clear understanding is not the end of wonder. It is the very foundation of true discovery. Our own place in the cosmos might be traced back to those ancient feeding frenzies. This line of thinking leads us to the Anthropic principle, a philosophical concept that suggests the universe we observe must be compatible with the existence of conscious life to observe it. The incredible energy pouring from the first supermassive black holes did more than just clear the cosmic fog. It fundamentally shaped the types of galaxies that could form. Their powerful outflows and intense radiation regulated star formation, preventing galaxies from growing too large too fast and potentially creating stable, long-lived environments. Without these early giants to stir the pot and impose order, the universe might have been a very different place, perhaps dominated by a chaotic sea of small, unstable galaxies. The specific chain of events that led to a stable spiral galaxy like the Milky Way, with its quiet suburbs suitable for planetary systems and life, may have been set in motion by the very black holes that seem so monstrous. This is not to say the universe was designed for us, but rather that our existence is a consequence of a very specific cosmic history, one that included the rapid formation of these gravitational titans. The solution to this astrophysical mystery is not just about understanding distant quasars. It is about understanding our own cosmic context. The same rare conditions that forged the first supermassive black holes may have been a necessary step in a long chain of events that ultimately led to us. This philosophical perspective adds a profound layer of meaning to the scientific quest, connecting the most violent objects in the universe to the quiet emergence of life. Each theory carves a different path through the impossible timeline, yet each reveals its own unique hurdle. The direct collapse model gifts us a ready-made giant seed, a perfect head start. But this elegant solution demands a cosmic lottery win, a pristine gas cloud bathed in just the right amount of radiation from a nearby galaxy, conditions that were likely fleeting and rare in the tumultuous early cosmos. Super Eddington accretion offers a thrilling growth spurt, a way to shatter the cosmic speed limit, yet this chaotic binge-eating faces serious stability questions. Can a black hole sustain such a gluttonous feast without the resulting radiation and powerful outflows, ultimately choking off the very fuel supply it depends on? The hierarchical merger model is a fundamental force of nature, the inevitable consequence of a growing universe, but relying on mergers alone to build a billion solar mass titan is like trying to win a race by constantly stopping to tie your shoes. The process is simply too slow to explain the quasars we see blinking into existence in the universe's first pages. Then there are the primordial black holes, an elegant idea that pushes the origin story back to the Big Bang itself. They would be the ultimate cosmic shortcut, but after decades of searching, we still lack any direct empirical proof that they exist at all. So where does this leave us? The most probable scenario is not a single winner, but a hybrid. Imagine an intermediate mass seed, perhaps born from a direct collapse or the death of a supermassive star. This seed then experiences periods of rapid super-Eddington accretion, gorging itself in dense, chaotic environments, all while occasional mergers with other black holes provide additional mass and funnel fresh gas into its waiting grasp. Different pathways may have dominated in different cosmic environments. In a dense protogalaxy, rapid accretion might have been the key. In a quieter region, a rare direct collapse seed could have been the foundational event. The true challenge for theorists today is to synthesize these ideas into a cohesive narrative, to build models that allow for this multifaceted reality. The puzzle of the ancient titans will not be solved by one single mechanism, but by understanding how all of them intertwined in the darkness of the young universe. This cosmic puzzle cannot be solved by a single field of science. The mystery of the early supermassive black holes spans the entire scientific landscape, demanding a chorus of experts. Cosmologists map the grand stage of the infant universe, charting the distribution of dark matter halos and the initial conditions that set the cosmic table. Particle physicists probe the fundamental nature of reality itself, questioning whether dark matter could have unique properties or if those elusive primordial black holes were forged in the first moments of time. Their work explores the exotic possibilities that lie beyond our standard models. Meanwhile, astrophysicists specialize in the chaotic mechanics of the feast. They run complex simulations of gas dynamics, modeling how turbulent flows of primordial hydrogen can collapse or fragment, and calculating the intricate physics of accretion, disks that funnel matter toward the void. And threading through it all are the relativists, who wield the complex mathematics of Einstein's theory to understand the severe warping of spacetime around these massive objects and the gravitational waves they emit when they merge. No single group holds the master key. A breakthrough in understanding the initial seeds might come from a particle physicist's equation. A new insight into rapid growth could emerge from an astrophysicist's simulation of a magnetized plasma. The solution will not be a solo performance, but a symphony composed by many. This collaborative, interdisciplinary spirit is the true engine of discovery, proving that the greatest cosmic mysteries can only be unraveled when we combine our perspectives. We have reached the edge of our current understanding, a frontier where cosmic history is still being written. Our journey has revealed not one single path, but a tapestry of possibilities, each weaving its own thread into the grand narrative. The direct collapse of pristine gas clouds, the frantic assembly through violent mergers, the exotic loophole of super-Eddington accretion, every theory offers a compelling piece to the puzzle. Yet the existence of these ancient giants is far more than a mere curiosity. It stands as a fundamental challenge, a cosmic question mark that probes the very limits of our physics and forces our models of evolution to adapt. We are now living through a revolution in observation. With every new deep field image from the James Webb Space Telescope, with every gravitational wave signal detected, we gather more pieces. We stand on the brink of discoveries that will not just refine our current theories, but may well shatter them, forcing a complete reimagining of the cosmos's first chapters. This enduring mystery of the early supermassive black holes is a profound reminder. The universe, in its infinite creativity, is always more wondrous, more complex, and more surprising than we can possibly conceive. So keep looking up, for the next great revelation is written in the starlight, waiting for us to